Hey everyone! In this video, we're going to primarily focus on reviewing trigonometry, so the whole unit altogether, just to make sure you're ready for the quest you're taking this week. And additionally, you'll see I have some special guests because it's a big week for me personally because Scooby-Doo comes out on May 15th. That's this Friday, so I hope some of you guys are going to watch it too. So we can definitely discuss that later in the week. But for now, just enjoy the slides that have been a little bit extra flared up with some Scoob pictures. So we'll see in number 1 here, a ball is attached to a spring, which is stretched and then let go. The height of the ball is given by the sinusoidal equation, y equals negative 3.5 cosine 4 pi divided by 5 t plus 5, where y is the height above the ground in feet, and t is the number of seconds since the ball was released. So the first part of this question is saying, at what height was the ball released at? So what's happening by the ball being on a spring is that we're going to push that spring down and the ball is going to shoot up. So I know that my starting point is low because in front of the amplitude, we see a negative sign. So that means it's going to go low first, right? So we have this negative 3.5. But that by itself can't make sense. We're not going to start underneath the ground, but instead we have to use the midline, which is at the end here, that my vertical shift. So that tells me that 5 feet is the middle of our curve, and the lowest it's ever going to get is negative 3.5 from that. So when I add that together, we'll end up with 1.5 feet. Now for the maximum, it's that same idea. We're still going to use the midline, only this time, that midline, we're going to go up, so we're going to add the 3.5, add the amplitude. And then when we add the amplitude, we'll get our max height of 8.5 feet. And then we're asked exactly how many seconds does it take the ball to return to its original position. So remember, we need to borrow the frequency here because the formula for that is taking 2 pi divided by the frequency. So in this case, we're looking at 2 pi, divided by pi over 5. And I could plug that right into the calculator as long as I'm careful to make sure that 2 pi is divided by parenthesis 4 pi divided by 5. Basically, what's going to happen is we're going to get 10 pi over 4 pi because it's the same as keep, change, flip. But it ends up being 2.5 seconds, which means it takes 2.5 seconds for one full cosine cycle to be completed. And now we're going to sketch that, and we're going to label all of our pieces in here. So the first thing I always start with when I'm sketching is the midline. So I'm going to say that's about my 5 feet here. Then we're going to put in our minimum and maximum. So we have our 1.5 and our 8.5 feet. Now, our period, it's going to take 2.5 seconds to complete, but remember, there's 4 increments along the way that we care about. So, that being said, we're going to take that 2.5 and we divide it by 4. And we end up with 0.625 seconds for the first one. We end up with 1.5 when I add another one of those. And when I add that one more time, I end up with 1.875. And if I added it again, we'd be at 2.5. So now we're ready just to make our curve. So cosine, remember, starts either above or below the midline. Cosine, because it's a negative 3.5, we're going to start low. So there was my starting point. In the next increment, we get up to the midline. The next one, we go up to the next. Then we start working our way back down. Remember, something very important is that you curve this function. It is a sine or cosine curve. I don't want to see anything straight like that. No way. Okay? But that would be what our picture looks like. Now, part E kind of ties it back to an old topic that we've talked about. What is the average rate of change of the ball to the nearest hundredth on the interval from 0.5 to 1? So remember, that's not a coordinate point. That's specifically talking about x values because it's the rate of change. So I would have you plug that in. So just like that, plug it right into your calculator and see what we get. And when I plug that in, we're going to end up with that 0.5 is x, comma, 1.5008418. So I just don't want to round too soon. I'm going to keep that in there. I'm going to do the same thing and plug in the same way, only this time I'm plugging in 1. And I'll end up with 1 and 1.503367. Now that we have both of those values, the last thing for us to do is to do the average rate of change, which remember is the change in y's, subtract the changes in x's. So I'm basically doing the slope formula in there. So I want you to calculate that in your calculator. And when you subtract those two and divide it by our 0.5, we're going to end up with 0.00504983. And to the nearest hundredth then, we're going to get 0.01. Okay, so it's a very small average rate of change between that time, but that's okay. But that's why we save our rounding to the end to make sure we don't miss that 0.01. Now in the next one here, we have a sine function increasing through the origin can be used to model light waves. Violet light waves as a wavelength of 400 nanometers, over which interval is the height of the wave decreasing only. So I want you to just sketch an idea of what the sine curve should look like. So that's my midline that I just drew. So since it's sine, remember, we start on the value, then we go up, then we go down, keep going down, and back up. So basically, we're going to have an S shape, right? So one wavelength, remember, was 400 nanometers. So then that means each of these increments, since I would divide each of them by 4, that means this is at 100, 200, and 300. So we want where it's only decreasing. So the spot where it's only decreasing out of my options here, 100 down to 300. So choice 2. Okay, another graphing one on the axis below. Sketch at least one cycle of a sine curve with an amplitude of 2, a midline of y equals -3/2, and a period of 2 pi. Now, to make our lives a little bit easier, I always start with the midline, but I don't want to start having to deal with fractions. So I'm going to take this midline and I'm going to convert it into a decimal. So I'm dealing with -1.5. So I might make my axes go by 0.5s then, just to make life a little bit easier. So let's say, here's my midline. So I'm going to count by 5s. 0.5s, excuse me. Now, the amplitude was given of 2. So that means it's going up 2 and down 2 from the midline. Now remember, that's really 4 boxes because I'm going by 0.5s. But so there's our max and our min. Okay, so that's what would be a 3.5. Oops. Sorry about that, guys. I just realized that it was supposed to be at a -1.5. So I'm putting it down here as my midline. and still up. 2, which is 0.5, and down 2, which is a negative 3.5. Okay, so we have our max and our min and our midline. The period is 2, so it's 2 pi, so it's a normal cycle for us. We know there's 4 important spots along the way that we have to hit. And if that's 2 pi, then I would have pi over 2 pi and 3 pi over 2. So those are our ones that have not been shifted at all. Now, with sine, it always starts on the midline. It doesn't say whether or not the amplitude, if it was a negative or positive direction. So you really could have gone in either way here. If you go up and then down, that's fine. You could have also gone down then up, and that also would have been fine. Oops. We're going to have an S-curve that looks something like this. Okay, so again, if you went down then up, that's fine too, because it didn't talk about direction in this case. But it did tell us where our midline was. It told us the amplitude and the period. Now, explain any differences between the sketch that we just made and from what we would have here. Well, so far the midline is still the same. The only things that are different are this negative pi thirds. That's a horizontal shift, remember. So that's my horizontal shift. And it's pi over 3 to the right. Because remember, the right is when you have that negative in there. We also have some multiplication, which we didn't really talk about. Oh, but remember, that's just my amplitude of 2. Okay, so in this case, because I decided just to sketch it the way I did, there's no difference in my picture and having an amplitude of 2. But if you made yours the opposite and made it go down then up, then you'd have to talk about there being a reflection. So be careful if you didn't do that. Okay, so 4, we have another graph one. We're determining the amplitude, period, and frequency and the vertical shift of the cosine function. Right in there to find that middle spot between this. So you can see that we're looking at 4 total of the height. So if I draw my line in here, here's my midline. So that's my vertical shift. So the vertical shift is down 5. Okay. When I cut this space in half that I used to find that, there was total 4, but it means to go up 2 and down 2. So the amplitude is 2. Now, the frequency is how many times it occurs from 0 to 2 pi. So the frequency, I'm going 1, 2, it happened twice to get to 2 pi, which was here. Okay, and then remember our period is always just 2 pi divided by that frequency, which is pi. And in this case, it makes sense because look, 1 full cycle finished by pi. So I could have also just looked at that part of the graph. Okay, so in this one, we're going to sketch 1 cycle of cosine. So I'm going to pause the video and then let you try this here. The picture or the question I got, the amplitude was 3. Period was 2 pi over 3. So the increments we would just divide by 4, which ends up being pi over 6. So I can show those in here. I know it's going to pass through the 0.04. So that's how I know it's going to start up for this cosine graph. And then we're going to make our way down. And make our way all the way down, back up to the midline, and back up, making sure to curve it. So make sure there's got some curve feature to this one for number 5 when we're making that sketch. But you use half pi, we didn't need the frequency in this case.